Hello everyone, welcome to my presentation. Today, I'd like to share my new tool named as IDA2Obj. It is designed to implement the static binary instrumentation. First, let me make a simple self-introduction. I am a security researcher from Trend Micro. My main job is analyzing all kinds of malware on Windows platform before, but now I mainly focus on the macOS and iOS platform. I started to dig zero-day vulnerabilities since last year. Currently, I have submitted more than 80 vulnerabilities to ZDI and got more than 50 CVEs acknowledged from Apple and Google. I also enjoy finding the root cause of some weird issues by reversing and debugging. IDA Pro is one of my favorite tools. Last but not the least, welcome to follow me on Twitter. My Twitter ID is Patchit. This is the background of my topic. Nowadays, many popular fuzzers are code coverage guided, including AFL, HomeFuzz, Syscaller, and so on. It's a piece of cake for open source project because we can just add some special options to compile to do the instrumentation. But how about the closed source binaries? DBI is the most choice, such as DynamoReal, Frida Scholar, and so on. But I think SBI is cooler and faster. Actually, there are some existing SBI tools, but it seems no perfect solutions yet. And I have new ideas for the implementation. So, what is SBI or DBI? The full name is Static or Dynamic Binary Instrumentation. Instrumentation means the act of adding X code to a program to measure its performance, diagnose errors, and write trace information. Binary means analyzing program at machine code level without having access to the source code. Dynamic means analyzing program at runtime. Static means analyzing program at compile or build time. We can see the compile instruction as the special case of SBI. So SBI is as fast as compile instrumentation in serial. Next, I will describe how I implement the SBI step by step. Well, let's start from scratch now. This is my first idea. We can load the binary into IDA Pro first and wait for the auto-analysis. When the analysis is finished, export it to the assembly file, which can be seen as the source code at an assembly level. Then, we can simulate the instrumentation process of compile. So, we got an instrumented assembly file. Finally, we can build the assembly file to generate a new binary. This is my first solution, just for PE binaries. I implemented another tool dubbed as IDA2MASM. The input and output are both PE binaries, and the assembler is the MASM from Microsoft. Now, let's export the assembly file. We can export all instructions to one assembly file by using IDA menu, File, Produce File, Create ASM File. However, MASM may cost many hours or days to assemble one ASM file. Luckily, we can use the script API to export from an address range. One more tip is, before exporting, we should use the IDA menu, unhide all. As just said, MASM has difficulty to process one big file, so we must split them into small ones. Splitting by segments is a good choice. We should manually load all segments, including header and the resource segment. Then enumerate all segments to dump, except for header and the relocation segment. Segments may share the same name, so just append their address to be unique. After the segments splitted, we need to process symbol reference. In MASM, we can use the keyword public to expose a symbol to linker explicitly. Especially for the labels, we need to note the double colons. And we can also declare the external symbols by using the keyword extern. Here is the symbol example. We can see there is a cross-reference from the pdate segment to the text segment. Then in the pdate assembly file, there is a declaration, and in the text assembly file, there is the public keyword. Note the double colons here. So this is the processing logic. First, scan all the items from minimum address to maximum address. For each item, get all cross-reference list to its address. If there is no cross-reference, skip the item. Otherwise, make the name public. For each item in the cross-reference list, if it is not in the same segment, add an external declaration for that item. After got the assembly file, we can insert some assembly instructions to do the instrumentation. Here is the code to find the instrumentation points. Scan all functions from segments. For each function, scan all code blocks. For each code block, make a comment, instrument here, as a hint. During the post-processing of the assembly files, insert the trampoline instructions before the command string, instrument here. Now is the time to reassembler, which is the most difficult stage. There are too many grammar errors to handle, and this cost me lots of time. I have written a Python script to do them all during the assembly file pre-processing stage. And there is another limitation for the symbol length, so I have to rename the long name to a short one. MASM is too ancient. Maybe I should consider try other assemblers. There is a longer list to tune the grammar. Here is just a small part. Note that I have to change all the short jumps into the long jump, because it may break the short jump range limitation after the instrumentation. Now we got some OBJ files from the assembly files now. It's time to link them all. This is the key issue at the linking stage. The API symbols from the import table are undefined, we must link with the proper lib files. But for some special API, I don't know what's the lib file to link with. Maybe some import symbols are from private SDKs, while we don't have the private libs. So we must generate the lib files by ourselves. Fortunately, I found the lib.exe from Visual Studio Toolkit have the function to generate lib files according to the DEF file. So this is the solution for the link issue. I just enumerate all imported models and create a DEF file for each model and write the import symbols into the DEF file. Finally, call lib.exe to generate the lib file from DEF file. After the linking stage, we got a new binary. But there is one more step to run. We need to patch the PE header, such as date directory. For example, we need to patch export date directory to make it port to the location of the symbol export dir. And we need to patch exception date directory to point to the location of the symbol exception dir, and so on. And then we need to fix the data entry in the resource segment. The data entry value is relative to image-based address. All of these fix operations are in one script for automation. Then we can run and test, but I got some crashes. There are three kinds of issues that lead to the crashes, all because of the incorrect analysis result from IDA. First is the unrecognized pointer, such as DQ offset a symbol. The second is unrecognized image-based relative value, such as DDRVA a symbol. The third is the unrecognized function-based relative value. It is a compression-encoded value for the exception handling. I will talk how to fix these issues later. IDA2MSM now works fine, but it's not suitable for full automation due to some corner case of grammar tuning. Thinking deeper, I have another idea. Let's think of the essence. A binary can be divided into two parts, the code and the date. For the code part, there are two kinds of instructions. One is the pure machine code, such as push or move. The other kind is like this: jump a label, call a function, and reference a data segment. For the data part, it's similar. The pure machine code has no cross-reference, which means it can be dumped directly. The rest instructions has cross-reference, which means it needs to be fixed for the symbol reference. Therefore, one binary can be divided into two parts, the green part and the red part. The green part can be dumped directly. However, the red part has symbol references, which need to be relocated. So the key point of SBI implementation is finding out all the cross-references, which are represented by the red arrows in the picture. And the main task is to fix them all correctly. So this is my second idea. Scan all the instructions from minimal address to maximum address and record their addresses as the old coordinate system. Then during the scanning, output the machine code for each instruction. If the instruction has no reference, output is machine code directly. Otherwise, output is the OP code first. Then output dummy bytes as a placeholder, and record its address and reference type into a fixed table. During the scanning, insert the trampoline instructions before the instruction with the comment hint instrument here. After the scanning, the size of the temporal output binary file will be larger. Then we will compute the new coordinate for each instruction in the temporal binary file and record them as the new coordinate system. Then we need to fix the placeholder according to the fixed table and the new coordinate system. Finally, we got a new instrumented binary file. Next, let's review this idea. It rewrites the binary directly, regardless of the file format. So it could be cross-platform in theory. The key point is fixing all the symbol references or regulations, and it seems too complicated to implement. Let's thinking of IDA2 again. What does the MASM do? What happens during the build process? Why don't have to fix the references manually during the process of IDA to MASM? MASM just translates the assembly to machine code and adds the symbols to the OBJ file. Actually, it is the linker that helps to fix the symbol reference in the final binary. So, can I directly generate the OBJ files and make the linker help me to do the fix again? This will bypass the damn MASM and avoid fixing the symbol reference manually. So my second solution comes. The tool IDA2Obj is used to do this. The difference from the first solution is in the middle part. I will directly dump the OBJ files instead of the assembly files. OBJ file is common object file format, and this is the file structure. First is the file header and option header, then section headers. The row date is used to store the executable code and the initialized date. Then is the relocation information. Symbol table and string table are at the end of the file. After making sense the file structure, we can write a tool to generate the OBJ file. Luckily, I found a repo on the GitHub which meets my demand. Avoid reinventing the wheels. The install process is simple. Just use the pip command. And here is the symbol tutorial for the Python library. First, create a module object first, and then create a section. Write the machine code to the section. Then add the section to the module. Next, create a symbol record and set its value to point to the offset inside the section. Here is 0. Then, add the symbol to the module 2. Finally, serialize the module object into the test.obj file. Next, I implement a class stackDumper to encapsulate some primitives. AddString method is used to add a askString to the string table. AddSymbol method is used to add a symbol record. It will call the AddString method. AddRelocation method is used to add a relocation record. Public symbol method and a reference symbol method will call the method above. The class stackDumper has an abstract method, fieldData. CodeStackDumper and DateStackDumper are the subclasses of the stackDumper. They just override the fieldData method to implement the dumping logic. Both the dumpers have the similar dumping flow. It iterates all the instructions inside the segment, stacked by the current item size. And if the current item has a name, it will public it. Then it will compute the cross-reference list. If there is no cross-reference, it will call the API getManyBytes to dump the data directly. If there is one cross-reference, it will dump the symbol with its reference type. And if there are multiple cross-references, it will dump many symbols and with their reference type. During the dumping process, if it meets the hint comment string instrument here, it will insert the bytes code of the trembling instructions and then increment the new address pointer. It will use the link.exe along with the Visual Studio 2019. There are several arguments for the BAT command. The first argument is the module name. The second argument is the output binary type. It's a dynamic library, an application, or kernel driver. The third argument is the payload type. Choose AFL payload or trace payload. The remaining arguments are optional to the linker. Now it's time to integrate with WinAFL. The key point is passing the bitmap area to the instrumented binary. AFL uses the API createFile mapping to create the shared memory. Harness uses the API openFile mapping to fetch the shared memory. I just do some modifications from a good example. This is the symbol architecture diagram. One more tip is enlarging the map size when you instrumenting more modules. The function AFL maybe_lock is implemented in AFL payload.assembly, which will be linked into the target binary and will be called at each code block to collect the code coverage. The main algorithm is the same as the traditional AFL further. By the way, it supports the multiple threads and multiple modules. FL previous locations is an array with the thread ID as its index and will be cleared to 0 before each fast iteration loop. FL area pointer is exported and will be set to the shared memory address by the harness. The harness is simple enough. Init function is used to do some initializations before fuzzing. It sets up the shared memory and named pipe. Pre and post functions are called in each fuzzing iteration loop. Here is the code to fetch the shared memory address into a global pointer. Init target function will set the AFL area pointer to the shared memory address for each target module. Now it's demo time. I will play the video recorded before. This is the demo for my tool, named as IDA2Obj. First, clone the code. The repo is private now. I will open source it later. I just put the code on the desktop. Then create a workspace, such as demo. Then copy the target binary, which you want to fuzz, to the workspace, and then load it into the IDA Pro. Note that you should choose menu load and load resources. It asks me whether to load the PDB file. Yes. The tool still works without PDB. Okay, auto analysis is done. Then execute my script. First, I want to execute libimports.py to generate the lib files. Done. Let's check the lib files. We can see there are 32 lib files, which corresponding to the import table. Check this one. These are the import symbols from the import table. Next, execute the script to dump the OBJ files now. Select main.py. Okay, the dump is finished now. Let's check the OBJ files. Yes, let's link these OBJ files into a new binary. Just use the link command. We will see the new binary is generated. One more step is to patch the binary. Okay, the patch is done. Let's load it again. Then we will try the new generated binary for fuzzing. Just back up this one. Replace to before the fuzz, we can use the command to check the instrumentation. Yes, we can see captured 794 tuples. Next, we will test multiple binaries. And this plus. Okay, we can see we captured more tuples now. Then run the fuzz command. The R disk is the RAM disk I just created. There are 4 copies, and make the output auto directory. Then run this command. We can see the fuzzer is running now. Before ending the demo, let's check the new generated binary. We can see in each code block, there is a piece of tracing code that call ACL maybe log. And this is the code we write in the payload assembly before. Thanks for watching. Okay, let's come back. Let's make a summary. First, I just let the linker help me fix the symbol references. However, the linker also generated some redundant data, such as the PE header. which makes me can't reuse the old PE header. Maybe I can hijack link.exe and only exploit its functions of fixing symbol relocations. Second, it could be cross-platform in theory, but I just make it come true for 64 platform PE. It is as fast as the compile instruction with the source code. Finally, the new binary could be equivalent to the old one, only if all the cross-references analysis is right. So, the real challenge coming. The challenge is the precondition of the solutions is that the analysis result from IDA is correct. However, for some reasons, sometimes IDA can't recognize some pointers or relative values, and it may lead to some crash issues. The solution is creating assistant scripts to help IDA analyze before exporting. The script is used to scan suspicious pointers from data segment. It reads a keyword value. If the value inside the PE address range, then it is a suspicious pointer. This script is used to help some relative values. There are some image-based relative values not recognized, many existing in the jump table of switch case. The fixed logic is a bit of complex. Maybe you will cost some minutes to read it. But now let's check the fixed effect. We can see the difference in the red rectangle. It was immediate value before, and it will get the correct cross-reference after the fix. IDA is supposed to analyze the exception handling data structures since the version 7. However, there are still some data structures that can't be recognized. Maybe because of the undocumented data structures. There are some function relative values in sh4. The core logic of the script is writing a parser according to the referred header file. Here we can see the data reference is recognized correctly after the fix. C++ frame handler 4, dubbed as FH4. It is a new feature to reduce the binary size of C++ exception handling on 64 platform. Some function relative values are compressed and saved into RDate segment. The relative values will be larger due to the instrumentation. So it means the RDate segment could be enlarged too. It compressed the value into 1 to 5 bytes, depending on the value. These two functions get net encoded, and decompression are used to decompression and compression. The solution is simple. I just rename the compressed location to the concat of a hint string. Fix me and the two targets address string. Then update the real value when the target address changed. Takeaway: I just introduced two static binary instrumentation implementations. One is IDA2MSM. The other one is IDA2Obj. And then I introduced one SBI algorithm. It just rewrite the binary directly. It could be cross-platform in serial, and it is not implemented yet. Then I wrote some IDA Python scripts to assist the analysis. The repos will be open source later. They are private now. Future plan: first, maybe I will do some bug fix. Welcome to report issues and pull requests. Then I will try to integrate it with other folders. Finally, maybe I will try to make the cross-platform idea come true. This is the references list. Thank you. If you have any questions, you can touch me on Twitter or email me at mickeyjin@trendmicro.com.